Hi, welcome to the Calculus 3 lecture series. And multiple integrals. So we're going to take the integrations of more than one variable. Okay, so this is our lecture number 3 here. For the previous two lectures, we talked about the double integrals over the Cartesian points. And now we are going to take a look at double integrals, polar coordinates here. Okay, so how do we do the double integrals? The polar coordinates. Okay, so let's go back. Let's go to our the lecture notes, and before we even talk about that, so let's start to do a very quick review. So far, we're dealing with the integrations and the derivative. We're all dealing with Cartesians, right? Coordinates. So what is the Cartesian coordinates? So for the previous two videos, we talked about the double integrals, right? So that means our integration regions. Okay, so we talk about the double integrals. So that means our integration regions are two. That means if it's in the Cartesians here, that means it's over the x and the y axis, right? So this coordinate plane, we call this a Cartesian coordinates. And we are quite familiar with this because that's got to remember since we were very young. We talk about this is a Cartesian planes, right? So for any point here, we said this is the point. So we use this notation x and the y's, right? So this is a coordinate point. So the first one is the value of x and the second one is the value of the y's here. So we all know this, okay? So now we say, okay, let's expand it. So how do I do this in the polar coordinates? And why I want to use polar coordinates, because like I mentioned at the beginning of the lecture for this calculus, for this unit is, the unit, for this multiple integrals unit, we not emphasize the integration technique, like U-sub and those things. We are trying to find the different way to simplify the integration. So from the polar coordinates, and for certain type of the function, when you try to take the integration, if you change to the polar coordinates, it will be a lot easier, all right? So what is the polar coordinates? It's a little bit different than the, okay, so than the Cartesians here. So polar coordinates, we have a pole, okay? And then we call it is the polar axis, okay? So this is here, we call this the polar axis, kind of like a y-axis and x-axis, right? And then any points, right? So any points in the polar coordinates. So how do we write it? We write it as the r and angle theta here. So what is the r here? So r, okay, so we say the r is the absolute value of r. So the length of the r is the distance, right? Okay, from the pole to P. So if this is, I say this is a P, that means it will be the distance from the pole to the P here, okay? And so what is the angle theta here? This is a measure of the directed angle. So this is a directed angle. That means this angle does have the directions, right? So it's a counterclockwise. And the width is the, the initial side. So initial side starting at the polar axis. Okay, so for examples here, so if for here, okay, so if here I have a point here, right? So let's say here, if I have a point here, this is the P. Okay, so that means this is the angles, right? So this is the angle if you do like this, right? So if this is 30 degrees angle or pi over 6 here, then the length is here. So this is like 1, 2, 3, 4. So the length here is 4, right? So that's why we say that this one is because it started with the polar axis, right? So this is so this is what this is the polar axis here, right? Okay, so that's how do we write this point? So how do I write the point here? Will be 4 and the what? I over 6, right? That's how do I write the polar coordinates, okay? So now this is what is the new coordinates, right? So it's the polar coordinates. So then we need to take a look, how do we take the integration over the polar coordinates? Okay, so let's go to here. So this is just what we did, what I did, and here's a summary for you. Right, so you have a pole with a pole axis, and this is the distance, and this is the angles, right? Okay, so now let's take a look at this one. So let's take a look at the first example. Let's get familiar with the polar coordinates. Now we take a look, how do we take the integrations here, right? Okay, so this one's here. We say, hey, let's try to plot it in the polar coordinates. How do I? So let's say this is the C here. This is 1, 2, 3, 4, 5. Okay. So now let's say the A is 4, right? So this is 1, 2, 3, 4, and there is a pi over 3. So that means here you go up here. So this is maybe it's not that much. Okay. So like that means you go up here, right? So this is 1, 2, 3, 4, right? So this is my what? This is my A, right? So A, so this is my point A here. This is 4 and pi over 3. So let's see here. See here you have the 4 lengths and what is here? This is pi over 3, right? Okay. Now the B, let's take a look at B. B is equal to, let me get rid of this one here. Okay, so the B is negative 3 pi over 4, right? Okay, 3 is here. So let's do like here. So if I do this way, okay, so this is 1, 2, 3. Okay. So then this point here, right, then here I have pi over 4. So this point will be 3 pi over 4, correct? But I'm looking for is a negative 3. So this is this direction 3. So what is where is the point of B going to be? Point of B is going to be here, right? So it's 1, 2, 3. All right, so here going to be point B is here. So this point here will be what is negative 3 pi over 4. Okay, right? Okay, so now let's take a look. The next point here is that is just 0. That means R equal to what? R equal to 0, and the angle is 3 pi. Okay, so I know the angles here, if the whole circle, if you turn the whole circle, going to be what? Going to be like 2 pi's, right? So you turn one more here. So basically, you turn one more, you're going to land in this axis, right? You're supposed to see here, right? So you have like 2 pi, and then you turn one more pi, supposed to land on this axis. But because, the R equal to 0, so what is here? So this is my point, right? So here, that's why I said this point here, right? So this point is my 0.6 here. Okay, now let's take a look at the next ones here. So the next one I have angle is negative pi over 4. I know if I rotate my angle counterclockwise, it's positive. So now I'm going to rotate, like the clockwise, so it will be negative. So here, this will be here, right? So this is pi. This is negative pi over 4 because from here to here, this is pi over 4, so it's clockwise, so it's negative. Now, what is the length? Here's 2, 1, 2. All right, so this is the point. So this is the point, right? So this is the point. It is 2 and negative pi over 4. So this is the point. Is what? Is my point of what? Is my point of this. All right. So that's how do we know that it's the polar coordinates. Okay. So now the next one's here. They say find the two other polar coordinates for the point. It's polar coordinates 8 and 8 pi. The pi over 3. What's that means here? So that means okay. So with the polar coordinates, right? So in here I have a pole here. So it's 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that means I swing. Okay, so this is I swing to here. This is pi over 3. So it's 60 degrees. So this is 1, 2, 3, 4, 5, 6, 7, 8. Right? So here, okay, so this is my point. Right? So this is 8 pi over 3. Right? So here, then they say find the other truth. So how do I find the other truths here? So the first one here, you can say, okay, so one way here you can do is, hey, you can just like do what? You turn, you say, okay, I turn the whole 360, correct? Then I can go boom, come back. Right, so I can turn this angles here. What is this angle? Is 2 pi plus pi over 3, right? So you turn this whole 307 pi over 3. So I know I can say 8 is 7 pi over 3 will give you the same point here, okay? And now, or let's see here, I say, hey, I can find another one, and this one here is, let's see this one is true or not. I say I can find another one, I say this is negative 8, 4 pi over 3. Okay, 4 pi over 3 is here. Let's see here, that means I'm going to turn, so this is 4 pi over 3, right? So that means this is pi, right? Pi plus another what? Plus another what? Pi over 3. So that's basically, I'm turning to here, right? So here, so look here, right? So if I use the color coding, so here, this is the pi, you turn, then you add another pi over 3, right? So here, this is pi, another pi over 3. So this is 4 pi over 3. Then the 8 will be here, right? So 8 is 1, 2, 3, 4, 5, 6, 7, 8. So this one here will be 8, 4 pi over 3. But in order to find my original point, so that's why I flipped back. So that's why the negative 8, 4 pi over 3. So if here, right? So for this one here, if you put a negative 8 in front, what happens here? Boom, flip back to here. That's what flipping back to my original. So that's why this one will make it. So as you can see, for the polar coordinates, right? It's not unique. It's not like the Cartesian is unique. This is not the same location. You can have many, many different points, right? All right, so let's take a look at the other ones here. So here, let's see here. Let's see that this is kind of a little bit of concept problem. Let's see. They said, hey, the polar coordinates of point are unique. We said never. Just like we see before, every time you turn another 280 degrees, another 360 degrees, it will be the same point. So then B said that here R theta and R theta plus 2 pi. This will always be equal? Yes, because that means it doesn't matter where is your theta. If you turn the whole circle, it's another 2 pi here. Okay, so now the next one is here. Let's say is r theta is always equal to the negative r theta plus pi. Yes, this one is always like demonstrated from the other because of when you add the because here for any r, right? So for any r, here this is my r, right? So and this is my angles here, right? So for any r, if you add a pi, the whole pi is go over here, then go over pi, go over theta here, right? So this is the theta, right? So that's why it's always what we say. So the part D, they said r theta equal to the negative r theta. This is always true, never, or sometimes. This is the one we say this is the sometime. All right. So this is we call it the sometime. The reason why it's sometime in general is not true. It will be true if r equal to 0, right? So if r equal to 0, then the negative 0 is 0. So this is what we call it the sometimes here. Okay, so the next thing here is because we are going to work on the integration with the x and y. So we say, how do we, like change this to be the, put it into the polar coordinate, into the Cartesian coordinates here, right? So here, this is what we say. This is pxy is a Cartesian, right? And this is r theta is related to the polar. So that's why I'm color coding here. Px here, this is the x, right? And this is y. This is the y. So the green related to the greens, right? And then the r theta is this one here, this angles, right? Okay, so now we say, hey, we change from the polar to the coordinates. So how do I find the x and y here? So x is green, right? So x is y. So it's the opposite side. So it's r cosine. So the x is, x is here, right? So it's the r adjacent side. So it's r cosine. Now here's y. So it's the y. It's the opposite side of the theta. So y equal to r sine theta. Right? So this is how do we change from the purple to green. Then the same way you want to change from the green to purple, change from the Cartesian to polar. As you can see here, okay, so I want to find the theta. Hey, theta is y and x, so that is what? That's a tangent, right? So it's a tangent is opposite over adjacent. Now, what is the r? Hey, by x and y here, right? Is Pythagorean theory, so that's why the r squared equal to x squared plus y squared. So we need to know the back and the forth of these two because later when we do the integration, we might need to switch that and change the variables here. Okay, so be careful, right? So that's why I color coding the green here is x, y, the purple is the polar, right? Okay, now let's kind of get familiar with this. Then we'll be able to start to take a look at the integration part. Okay, so in here they say find the polar coordinates. All right, so find the polar coordinates for the point P with the rectangular, that's the Cartesians, right? So this is the Cartesian coordinates here. All right, so if this is a Cartesian, I know this is x and this is y, right? Okay, if this is x, this is the y here. So I know from a while ago we said the tangent theta is equal to y, so y over x, right? From the previous, this one, the graph here, right? So you change from the green one to the purple ones, right? So tangent theta is y over x here. So then we can see here. Okay, so now we will see here. These ones here will be equal to the y is 3 square root of the 3 over negative 3 is equal to the negative square root of the 3. Okay, so then we know the solutions here. So what is the theta? Okay. the thetas here, okay, be careful here, right? If you use your calculator, and so it will give you the negative values here. It will give you negative pi over 3 because they treat it as the inverse function of the theta. But in here, you need to know here, okay, so because of here, x is negative 3, y is here. So you know your point is here. Am I right? Okay, so you know your point is here, right? So this is the P point. So you know the thetas here, right? The theta is from here to here. Okay, so it has to be on the second quadrant. So if you put it into the calculator, what they were going to give you, they were going to give you theta is equal to the negative 60 degrees. So they will give you these angles here because they are using the, the inverse trig function to figure that out. So in here, you need to be careful to see where, you have your points, right? Okay, so now the thetas here, it will be the 2 pi over 6 here. Let me color code it. Okay, so this will be the 2 pi over 3. So it's 120 degrees here. Be very careful, right? Okay, so now I need to switch that to the, so that will be the, so then the r, so r squared is equal to the x squared plus y squared here. Okay, so the x squared plus y squared, so r squared is equal to the 9 plus 27 equal to 36. So r is equal to the positive 6 over negative 6. Okay, so now let's take a look here. We said the thetas here, right? So because I don't recognize this one is on the second quadrant, so theta is 2 pi over 3. So if 2 pi over 3, that means here this is 6, right? So the p here, I can write it as 6 and then 2 pi over 3. Okay, but we also can do this, right? So, but I have another value here is negative 6. So, like remember we say the thetas here, if you put it into your calculator, what they're going to give you, see here? They will give you the theta is equal to negative pi over 3, right? Okay, so if it's negative pi over 3, see here, you will see that means how your angle swing here is always on the polar, right? So this is the polar axis. You swing here. So this is pi over 3. Right? This is negative. You swing this direction, it's pi over 3. And then, like in here, you have like 1, 2, 3, 4, 5, 6. Right? So this will be the point. What is this point? This is 6 negative pi over 3. But if you want to use negative 6, what you can do here, you can boom, switch this one back, right? So how do you switch this one back? You add a negative, so you push this point back to here. So the same point you can write as negative 6, negative pi over 3. Okay, so you have 2 ways to write these coordinates. It's pretty cool, right? Okay, now let's take a look at problem number 5 here. The number 5, they tell you find the rectangular with the polar coordinates, negative 4, 5 pi over 6. Okay, so now let's take a look at what is this one going to look like. Okay, so, the first one's here, 5 pi over 6. So it will be 150, right? So it's 150 degrees. So, okay, so this one's here, that means I swing, right? So I swing the 5 pi over 6. And now, this point here, this is 1, 2, 3, 4. So this point going to be what? It's 4, 5 pi over 6, that's right? Okay, so this point will be 4, 5 pi over 6. So, but it says negative, so what's that mean? That means I'm going to what? Boom, reflecting that one back, right? 1, 2, 3, 4. So that means I'm going to have a point here, right? So this point, what is the code is -4, 5 pi over 6. So this is the point given to us, right? So I'm going to find the x and the y. Okay, so in here, okay, so in here, let's see here. So I'm going to find the x and the y's here, right? So x here, okay. So the x here, it will be, depends how do you want to use the positive or negatives, right? Okay, so the x here is r cosine. Okay, so it's a -4 cosine what? 5 pi over 6. Okay, now, so here this will be the -4 5 pi over 6. So this is -4 cosine 5 pi over 6. It will be negative. I think the unit circle has the square root of the 3 over 2. So it's 2 square root of the 3. Then the y is r sine 5 pi over 4, 5 over 6 here. So this is a -4 and 1/2, -2. Well, that sounds reasonable. So this one, if you change to the Cartesian, it will be 2 square roots of the 3, -2 is the quadrant, fourth quadrant, right? So that is correct. So I know we did correct here. Okay, so now the next things here we're going to talk about. Okay, so now we get a pretty good understanding, right, about the polar coordinates. It's kind of also is a review here, right? Okay, so now, okay. So now we take a look at these ones here. We said let x be a region in the plane, right? F of x is continuous in this region. And this region is right now, I can use the polar coordinates to represent it. And so how do I convert this integration by using the polar coordinates here? Okay, so if you take a look here, right? So take a look at this graph here. Okay, so this is the regions I want to integrate with certain functions. See here, this is x and the y's here. If you use the Cartesian planes here, so x and the y, so here probably some x squared plus y squared equal to some numbers, right? So you need to integrate over these regions here. So we say, okay, so if I change to the polars here, say, take a look here. So for polars here, right? So I'm in between the two circles here. So in here, the R is what? R is fixed, right? So it doesn't matter where the R is always fixed. So that's why I can take integration. So the R here is from A to B. See here, that's the second one. I'm taking the derivatives. Now take the integration. Then for the zetas here, right? So remember, right? So remember that now I'm looking for the polar coordinates, right? So the polar coordinates, so like for example here, and here, and go here, go here, and go here. What happened? Hey, your zeta is going to be different. Okay, so your zeta going to be, you know, like of course zeta be different. I said zeta going to be, you know, depends on these two curves here. So going to base on, so when you touch these two curves, and then your angle zeta will be depends on the curves, right? So like in here, so why did it disappear here, right? So like in here, that means that when your zeta is here, right? So you touch here, this will be, so this angle will be determined by this point, right? So then you touch here, this angle will be decided by this point. So that's why the zeta is a variable, right? So that's similar like when we do the double integral for the type 1, type 2 regions, right? So this one is the same type 1, type 2. So theta is between the two functions here. So that's what we say theta is between the two radius functions. So that's why we say the d theta's here. So you're integrating along the two functions here. Then you substitute your fxr, x you substitute with, so the x you substitute with r cosine theta, right? And y you substitute with the r, y sine theta here. Okay, right? Then if you pay attention, you will see there's one little thing extra, right? So this is one little thing extra, this little r. Okay, what is this little r? And I'm going to, so this little r, we basically call it the Jacobian of this transformation, okay, for the transformation. And I'm not going to show you how to get the r from right now, and but later when we go to the next sections when we talk about the triple integrals, and when we try to find the Jacobian for the triple integration transformation. So for example, if I want to transfer the R3 into the cylindrical coordinates, then we have a Jacobian, then we're going to formally define the Jacobian. So just remember, right? Right now, let's take it for granted. When you do the transformation for the polar, you always need to times the r, and r is our Jacobians here. Okay, so now let's take a look at this ones here. So the second ones here, you see here, right? The r is a function, but the angle is fixed. It's from r alpha to beta, right? So that's why you integrated the theta first here. Now you reverse it. Okay, so now because the r is a function, right? So r is a function because right now the radius r here depend on these two functions. So that's why the r, I have the two functions of the theta. Then the same way, you plug in the cosine theta, I sine theta for the x and the y, and then take a look, I also have this, right? This is what we call it here. This is what we call the Jacobians, right? Okay, so let's leave there. Okay, now let's take a look at how do we do this. It sounds pretty complicated, right? Okay, in fact, this is not. Okay, so now in here, I want to integrate. So this is, okay, so I want to integrate this ones here over the d. So this integrations here, right? So this is x dA. So this is the d. This is the integration over the Cartesian. So of course, if this is a Cartesian, so you can figure out what is the formula for here, and just do the dx dy's, right? So that means in here, the reason why I say it's a Cartesian is because this integration is x, and you can do dx dy to whatever this region is. As you can see, this is not an easy region to integrate. So after you change the x and the y, probably will become pretty messy here. So now let's take a look. How can, maybe I can convert to the polar, okay? Okay, so now let's see here. So this function is really complicated. So like, I don't think you can even try to switch that. You need to use like a complete square method, and you try to find the boundary. Then your boundary going to have the square roots, and so it will be, pretty difficult. So let's say that, let me convert that. All right. So let's see. Maybe polar coordinates will be easy. So this is x squared plus y squared equal to y. So I know what is the x squared plus y squared. This is equal to what? This is equal to the r squared, right? And the y, what is the y here from the previous our definitions here? We say how to transfer that. The y is r what? R sine theta, right? Remember like we did here, right? So we say that x is the r cosine theta, y equal to the r sine theta, r squared is equal to x squared plus y squared, right? So here, okay. Now, okay, so now this one's here, we transfer that. So now here we say this is r squared equal to the r sine theta. So I can say r is equal to what? R equal to sine theta. Okay, and now if you try to integrate over this regions here, take a look here. So this is my, that means I'm integrating here, right? Right. So for each r, so for this is the regions, right? So I know this region, the theta is fixed. It's from 0 to I over 3 here. Take a look at this blue line. When I try to integrate, my r is what? My r is different. And where my r going to go? Say, hey, it's going here, right? Because this is the line, this is the curve, and I derive this to r sine theta. So I know this one I change to the r equal to the sine theta, right? Okay, so that means my r, my r is here, right? So my r going to be from 0 to what? To the sine theta. Okay, so now let's do the double integrals here. So this one's here, okay, so this one, x, dA, this is a Cartesian, right? Okay, now I can change it to the polar, right? So because the r is a function, so I need to do dr first. Then I need to plug in my function to the f of x, y. So this is this x, this is my f of x, y. So when I plug in, what is the value here? F of x, y, x. So x is r cosine theta, right? Then also I have, so this is common. So this is my x, right? Okay, and then don't forget, I need to have the other r. What is this r here? This is what? This is the Jacobian, right? Okay, that's very important. And then we said, all right, let's take a look. So which one I need to integrate first? I need to integrate dr. Why? Because dr is a function, right? So that's the variable. So I need to integrate the r out. Then I integrate the d theta. So what is my r's limit? My r's limit is 0 sine theta. So what is my theta's limit? Is 0 pi over 3. So this is how do I change to the, how do I change to the coordinates, right? Okay, so now in here to the polar. So now that you will see the integration, it's not easier. So this is pi over 3. Then you will have an r squared cosine theta, dr d theta. And then this is 0 sine theta. Hey, I'm only integrating r squared dr. Wow, that's pretty easy. So this will be equal to the 0 pi over 3, right? So cosine theta just a constant. Then what is this integration? 3r to the cube. Then I have 0 and the sine theta and the d theta, right? So you substitute and then this one's here going to give you the 0 pi over 3, and then this is 3 sine cube theta and the cosine theta d theta. Now you can use sub, and so the answer here so pretty easy, right? So this will be sine 4 theta and the 12, and this is 0 pi over 3 from here to here. What is here is you sub, right? And then you will get the answer is 3 over 64. So this is how do we change, right? This is how do we change the integration from a pretty messy Cartesian plane integration by using the polar, right? So that's why you will see the integration turns out pretty easy. You know, think about it. If you want to use a dx dy just from this limit, it's very difficult to do. Of course, you can say that if you want to, you know, like for here, you can say, you know, Cartesians, right? So basically, you can say, hey, I need to, right, do like this way from x here, right? So you can do from here this way. You need to figure out this line, and you need to figure out this curve. And probably it's very messy here. Okay, now let's take a look at our next examples here, right? Okay, so the next example, okay, so we want to rewrite using the polar coordinates here. Okay, so let's try to see here. This is the typical, what type of the integrations? This is a Cartesians, right? Because we have x, y, dy, dx. Okay, so now let's take a look at what in the area we are integrating. Okay, so be careful, right? So we kind of review here. This is dy, right? That means this is the boundary for y. So that means y is from 0 to x. Y equal to x is what? This one, right? So this is y equal to x. And then, okay, so the x is here. So the x dx here is from 0 to 4. That's what's that mean? That means the x is from 0 to what? To 4. So here, this is 4 here, right? I got it, right? So this is the area I'm integrating by the Cartesians, right? Okay, so this is y equal to x, so this is x equal to 4. So this is the area. So this is my area D. Okay, now let's take a look, right? Let's take a look. How do I change to the polar, right? So now here, the polar, this is my polar axis. I start to swim, right? So the swim here. Wow. So I swim to here. So I know, hey, here, I know my angle is what? Is fixed, is a constant. So I know my angle is from 0 to what? To pi over 4. Right? So it doesn't have a curve there. But, okay, now my r has differences. So this one says, this is my r. This is my r. My r was bounded by this function, x equal to 4, right? So this is my r's here. So this is 4's here, right? So I know, you know, I know the thetas here, right? So if you take a look here, so you know the cosine theta, cosine is what? Adjacent over hypotenuse, right? So it's 4 over what? 4 over r, right? So that means the r is equal to the 4 cosine theta, or you want to write it, you can say it's 4 secant theta. So now I know I can say, okay, now my r is from 0 to what? 4 secant theta, right? So I know here, okay, so this is the variable. So my r is a variable. So I need to rewrite this. Okay, so let's try, see if we can rewrite it. So which one I need to integrate first? I need to integrate the r first, right? Now, the x is r cosine theta, remember, right? So y is r sine theta, right? So as a plug into, so it's r cosine theta, r sine theta, right? So take a look, what is this? This is x, this is y, and don't forget what we have here. Don't forget this r. What is this r? Don't forget, this is Jacobian, right? Okay, and then we say which one I need to integrate first, and I need to integrate dr first, right? Now after integrating dr, I integrated d theta. So what is the r? R is 0 to 4 sec theta, and what is the theta here is 0 pi over 4 theta. All right. So in fact, this is not too difficult to integrate because you have r cubed, and then the r cubed, and it's easy to integrate, and then you substitute. Okay. So, but then here they did not ask us to integrate; they just want us to rewrite. Okay. So for these problems here, probably you use the Cartesians. It's a little easy because the regions make the Cartesian a little easy. Okay, so now let's take a look at the last ones here. So let's say define the volume of z equal to the x squared plus y squared over this given regions here. Okay. All right, so that means my function f of xy is, so that means my function f of xy here is x squared plus y squared, right? Okay. So now let's take a look here, right? So let's take a look. This is the region. Nice enough, they already changed to, to the polo for us. Okay, so let's take a look here, right? So if this is my polo, this is my polar axis. So when I swing, right? So when I swing here, okay, so now I swing here, this one here will depend on how the, right, how is this back. So I know if I swing like this one's here, so for this problems here, which one is fixed? Which one is fixed? It's my R is fixed, right? So R, the radius is always between these two circles here. So it's always between 1/2 to 1. Okay? But my thetas here, right? My thetas here, the angles here, when I do that, my thetas here is it depends. So measuring here maybe it's easier to see here, right? My thetas here is it depends where is the R here, right? So like for this one here, so for this one here, for this one here, right? So that's what is your theta going to change, right? So like here. So I know the theta is a function of R. So that's why I know the theta will be from 0 to 1 to R here, right? So I think for the polar, maybe the hardest one you need to identify is which region, which variable is fixed or which variable is not fixed, right? Okay, so let's take a look and see what find the volumes, right? So I want to find the volume. Okay, but what the Cartesian is, this is what we do. We say, hey, under the D, then this is x squared plus y squared dA. So if you use a Cartesian, this is D, then this is like x squared plus y squared dxy. Now you need to find the boundaries. So this part will be pretty difficult to find using the Cartesians, right? Okay, so I know the whole Cartesian is pretty difficult. So now maybe I will switch to polar. Okay, so let's take a look at switch to polar. Okay, okay, x squared plus y squared. So it's r cosine theta squared plus y squared. So we know this is what? This is r squared. Correct? So what is this one, right? This is x squared plus y squared. And also don't forget what is next. This is Jacobians, right? So this is my Jacobian. Okay, and now I need to know which one integrate. Oh, which one is variable? Oh, it's a theta. So I integrate d theta here, right? Then So theta is from 0 to r. After I integrate theta, I integrate r. So what is the r? So here is 1/2 to 1. So did you see we change a very, very complicated the Cartesian integration to a polar integration. Okay, so now this is the 1/2 is the 1. And then here the r cube you integrate with what? 4r to the what? 4th. Okay. Oh, I'm sorry. We are integrating theta first. Alright, so the theta here. So this is we have a r cube. So d theta, there's no theta here, so the integrator will be thetas, right? Okay, then you found the 0 to the r and the dr. And then see here how easy this integration is. It's 1/2 to the 1. So this is the r4 minus 0 dr. And so you will get this is the 5th the r5 1/2 and then something will be 31 will be the 160. Okay. Okay. So that's it. Okay. So the summary here is if you take a look, you know that the polar, right? So like this integration region. So if the integration region is kind of is the part of the circular, like this is like the part of the true circle. Then you know you change it to the polar is very simple, and because of that you can write it to the polar equation. So because they're dealing with like circles here, and then the like here the r square is going to be like x squared plus y squared. So the same ways here for this one here, number 7. As you see, this integration is not a circular, right? So it's a triangle. So probably you still can transfer that, but probably the Cartesian is what? The Cartesian probably is a lot easier than the polars here, right? So like this one's here, this is a circular, right? So this coordinate, you know, this integration region, right? This is the circular integration region. So the polar coordinates will be a lot easier to help us to solve the integration. You know, if you try to change this to a function, it will be pretty messy, right? Okay, so I guess that's the, you know, that's what is the polar coordinates can help. If your integration region is a circular shape, it doesn't have to be a total circle, but if it's a circular shape, then it certainly will simplify a lot. And also when you do the polar transformation, do not forget Jacobian transformation. So it's R, and I mentioned, I'm going to prove it and show it to you how do we get R to the time when we go into the triple integrations. When we talk about the 2 other coordinate systems. So now I'm going to show you what is Jacobian, how do we get Jacobians, all right? And that's it, and it's very interesting, right? It's fun, and we know how to do the double integrations by using the 2 coordinate system. One is our classical traditional Cartesian, other one is the polar, right? Remember the polar is if the integration region is a circular, part of the circle, then use the polar. Easy. All right, okay, that's it, and have a good day. And looking forward to our next topic, we're going to start the triple integrations. Okay, bye, have a good day. Okay, bye-bye.